So we're very, very happy and proud that Sophie Kriz accepted the invitation to join us in this conference. And got to know Sophie because she did a very nice work on equivariant homotropy Bourdism and showing some conjecture is false. An amazing job. But Sophie has other works that she wants to share. And so she decided to talk about the FImodules. So Sophie, thank you very much for coming. The floor is yours.
Oh, thank you very much for organizing this wonderful conference and for inviting me. So like Bernardo says, I'm going to be talking about some computations on FImodules. So first of all, let me define that, what I mean by that, and talk about some motivation of why that's important from algebraic topology. So let me consider these categories FI and ME, which are just objects are finite sets, and morphisms will be injections or bijections, respectively. So you can see that these have categorical skeletons coming from the just natural numbers and zero. And so I consider FI objects, which are just given as sort of functors, which are defined as functors from FI to some category I might like. So for example, R modules for some commutative rank R, or K vector spaces for some field K. And these actually appear quite very often in algebraic topology. And so one thing I can do with them is if I have two FImodules, where sort of the category I'm going into is nice enough, so I have some tensor product, which is distributive under some coproduct, then I can produce a new FImodule, this M box times N, called the day product, where just for a finite set S, what I do is I just take this coproduct over all ways of writing S as a disjoint union of two subsets, A and B, and just applying M to A tensor with N applied to B. And so so these commutative monoids with respect to this day product are called twisted commutative algebras, or TCAs. I believe this terminology is coined by Sam and Snowden. And in the case of representation stability, sort of the most basic example is actually quite important. So this is just this constant twisted commutative algebra Z, where just for every finite set S, I apply it and I get Z. And so the objects with a constant Z action are the sort of titular FImodules. Maybe another example which you might think of, which might be sort of more familiar or more important to the sort of audience here today, could be this just a sphere spectrum, which we do by, okay, there are many S's here. For a finite set S, I take this blackboard bold S of S to be this smash product of finite set S worth of S1s. And so objects with this action are the symmetric spectra. And so I already introduced this day product, which provides some symmetric monoidal tensor product structure of these FB objects, but I can also do something more interesting, which is this Kelly composition product. And this you can see here is given by, if I have two FB objects M and N, I want to apply them to some finite set S. What I do is I take the coproduct over all ways of decomposing S as a disjoint union of some SIs, where I runs through this indexing set T. And then I apply M to the indexing set T. And then I tensor with this big tensor product of N applied to each of these subsets Si. And so it's a theorem of Kelly that monoids with respect to this composition product of these FB objects are equivalent to operas. And recently, if instead of FB, you want to work with FI off objects, so functors from FI off to some category, there's also a based version of this theorem proved by Mei, Zhang, and Zhou. So that's sort of one context in algebraic topology where we see this sort of type of objects appear. And maybe another context which might come to mind is Siegel spaces. So here we look at script F instead of Fi or FB, which is this category of based finite sets and based surjections. So we actually, you can see that there's a natural inclusion from the opposite category of finite sets and injections into this stripped F. And that's just given by if I have some inclusion from T as a subset of S, I can make a base surjection going from S with a base point to T with a base point just by sending everything in the complement T to the base point. Okay, so here I'm going to introduce this notation. Just let N be this thing I was talking about, this sort of skeleton I was talking about earlier. Just let these be the sort of N canonically chosen, like sort of N element sets. And for all sort of N natural numbers greater than or equal to 0, for any choice of I in this 1 up to N set, we have a natural based surjection corresponding to I, going from N as this disjoint base point to 1 with a disjoint base point, just by sending this I to this point and everything else to the base point. And so then a Siegel space is a functor of an F space, so a functor from F to spaces, such that if I look at the induced map going from X applied to N, so sometimes I'll omit the square brackets when it's clear what we're referring to X1, which sometimes is just labeled X. Then if I look at these I's and I look at the product of these maps, which now goes from Xn to X to the N. So here it is important that it's really the Cartesian product, and this really is, it's important that it's spaces. So the Siegel condition says that this is an equivalent. So if this is satisfied, X forms the Siegel space. And sort of the point of these F spaces is that they provide a model of infinite loop space theory. And May and Thomason proved that they are equivalent to E infinity space. Okay, so those are some various contexts in which these sort of FI module-like structures appear in algebraic topology. And here's maybe a more geometric, more concrete sort of calculation where like the structure of FI module specifically is used, and it's in sort of computations of cohomology of configuration spaces. So basically, I can consider if I have some manifold M, I can consider the configuration spaces on M as an FI off space, just by considering conf N of M as embeddings from this N element set into M. And so there's a theorem proved by Church that if I have a connected oriented manifold of dimension greater than or equal to 2, such that if I look at this dimension of its cohomology, if its rational cohomology in this dimension is finite, then if I look at the graded FI algebra, which comes from taking cohomology of this FI off space. So in general, cohomology of an FI off space will always provide graded FI algebra. And I look at this rational cohomology, it turns out that it's of finite type. In other words, at each degree, if I look at the ith cohomology of conf of M, this is a finitely generated FI module. And so this specifically can give us some computational results and some sort of stability. So here, let me sort of look at this specific example where if I have of these sort of colored configuration spaces where I look at this, I look at some partition mu, mu1 up to mu k, such that n is greater than or equal to the total size of mu. Then I look at this space conf n mu of m, where sort of mu I of the points will be colored I for I going from 1 to k, and the rest of the points will be left uncolored. So I can ask, what can I see if I look at the cohomology of these colored configuration spaces? And so it was proved by Church, Ellenberg, and Farb that if I have a connected oriented manifold, dimension greater than or equal to 3, we actually obtain stability. So if I have the ith cohomology of this configuration space on endpoints with colors mu, then it's actually equivalent to the ith cohomology of the configuration space with n+1 points and colors mu. And so specifically, the exact method of proof of this, and there's actually also quite a few other applications. So like, for example, also to cohomology, to computations of cohomology of moduli spaces, for example. There are similar results. And the method in sort of all of these computations is by specifically looking at the structure of the FImodule. And so, in other words, representation stability. And it might be sort of conspicuous that we're always sort of working over a few these specific computation cases. And that's because sort of the classical story of FImodules really only sort of works well, or is sort of well known over Q. And so my work is to extend some of these sort of basic structural results which we have on FImodules over characteristic zero field to integral context or a positive characteristic field. Okay, so I'm going to just first give a sort of brief review of the representations of the symmetric group, because they're sort of very deeply related, as you can probably tell, to the structure of FImodules. So just recall that, okay, so I'm going to denote the symmetric group on n elements by sigma n, because there are probably already enough s's floating around. So the simple representations of this symmetric group on n elements over a field of characteristic zero, it's a well-known result. These are the Specht modules, and they will be associated or indexed by these unordered partitions lambda of n. So for example, here I have the case of n equals 7. So my lambda is 4, 2, 1. And I can represent this graphically using this Young diagram. So I'm using the English notation where the first row is the longest one and it's put on top. Okay, so I'm going to just go through like the sort of how we can sort of think of the Specht module in this specific case. It'll sort of be apparent how this generalizes. Okay, so basically what you need to do is you need to pick words such that on the one hand, you have one letter corresponding to each row with the number, with sort of number of occurrences equals the number of boxes in that row, and similarly for columns. So I think the Young diagram I have here is actually one of the only, possibly the unique Young diagram where you can actually use real words. So here I have bananas and referee, and I can arrange them like so. And these will sort of be like our basic choice of arrangements. And so if I look at these two arrangements, I can see that if I overlay them on top of each other, fairly clearly each box will contain a unique pair of letters. And so if that's true for two sort of choices of arrangements, we call them compatible. Okay, so the Specht module will be a sort of a submodule of the free K vector space on arrangements of letters referee into the Young diagram. And specifically, I'm going to want my generators to be sort of the sums of arrangements of referee, which are compatible to a fixed or a given arrangement of the other word bananas, such that I have assigned, depending on parity of that arrangement, with my original sort of choice of sort of basic arrangements. So for example, here's one case. I'm just looking at this basic arrangement of bananas, and I can see that this one is sort of my basic representation of referee, and it's compatible. So I give, and it's basic, so I give it a plus. And every time which I look at a different arrangement of referee, which is still compatible with this one, I look at how many sort of moves I need to make to get between these. Here it's just one move, so it gets a minus, and so on. Even though, and just something to note, you can already see that it's already quite a mess, even for this very small Young diagram, 4, 2, 1. it's very difficult to sort of hands-on work with this spec module. And I guess, so I guess more sort of generally, what you want to be looking at is the image of some sort of some map going from this quotient of sigma n over, I guess, let's see, over column preserving permutations to, with some sign, to this quotient over row preserving representation, row preserving permutations. And I want to, and my spec module will be the image of such a map. Okay, so over field of characteristic 0, it's very nice that these spec modules really are the simple representations. And in fact, so that's a semi-simple category, so we can think of representations as a direct sum of these spec modules. But over a field of characteristic greater than 0, this fails fairly badly. And what we can say is that if I look at each of these spec modules, I can look at a sort of quotient called d lambda, which I can think of like this. In the case when lambda is a p-regular Young diagram, meaning that I don't have a single row length which repeats p times, or p is a characteristic. And so you can, it's sort of a known result that these form in positive characteristic the simple representations of the symmetric group on n elements. So now over positive characteristic, things are no longer semi-simple. So what we can say is that all the finite dimensional representations will have some finite filtration where the graded pieces, where the associated graded pieces look like these d lambdas. Okay, so that's enough sort of background about the representation theory of the symmetric groups. So let me actually get to some results and sort of show why this is relevant. So sort of the key example of an FI module will be one which will be the so-called stable spec module. So basically what I do is I consider some Young diagram, some partition, some unordered partition lambda 1 up to lambda k of n. So I think I said this earlier, but the total size, I'll denote the size of lambda using these absolute values. And I can always consider, so if I have a natural number such that it's greater than or equal to this total size of lambda plus the size of the first row, then I can consider the sort of Young diagram I get by adding this first row of length m minus n before lambda 1 up to lambda k. This gives me a new partition now of m. So it's a result that there exists an FI module strict S lambda, such that if I plug in some FI degree, this finite set 1 up to m, then I get precisely this spec module associated to this lambda plus this first row of length m minus n, when m is large enough for that to make sense, and I get 0 when the degree is too small. So here is just an example of the stable spec module associated to this very small Young diagram 2-1. I can see that the first occurrence of something non-zero has to be in degree 5. And as I go on, I just keep adding to the first row. Okay, so the FI modules themselves maybe aren't actually categorically so interesting, because the simple objects just in the category of FI modules will sort of just look like, at least in the characteristic 0 case, will look like a spec module just concentrated in the degree in which it makes sense. So that's not really telling us anything about like stable effects or anything. So we need to take a more specific category. And so we need to introduce the idea of a torsion in generic FI modules. So basically I consider if I have an FI module V now, I can look at the elements in some degree of Vn, such that I can look at such if there exists some larger big N, such that if I look at an inclusion from little n into big N, this element will be killed by the induced map from B little n to B big N. And so these, if I sort of collect these torsion elements together, well, one can see that they actually form a sub FImodule of V, and denoted by T of V. So it's a functor from FImodules to torsion FImodules, where I call an FImodule torsion, of course, if it is just its torsion. So denote this category by T FImodule. And so torsion FImodules are precisely the things which are boring to us, and which don't showcase any sort of never ending effects. And what we're going to do is we're going to take the Serre quotient of FImodules by torsion FImodules. And these are the so-called generic FImodules. And so these are precisely going to be in some way somehow they're going to capture like the never-ending effects. So in like these results of Church, Ellenberg, and Farb, they sort of exactly look at these sort of this generic FI structure, and they look at sort of how it decomposes into simples and to do some combinatorics to show some dimension effects. And so I guess so one can ask precisely what will be the simple objects of this category we get from this quotient of generic FImodules. Okay, so in characteristic 0, it's actually quite nice because it mirrors exactly what happens on the representations of symmetric groups. And it turns out, so by a theorem proved by Sam and Snowden, that the stable Specht modules script S lambda will precisely be the simple objects in the category of generic FImodules in characteristic 0. So in positive characteristic, we actually get something somewhat similar. So there will be certain FImodules, let me call them script D lambda, associated to these simple representations we get D lambda for a lambda p regular Young diagram. So it's a theorem proved by Nagpal, but I found a sort of precise construction which we can sort of get our hands on in positive characteristic of these script D lambda, these FImodules for lambda p regular Young diagrams form exactly these simple objects in the category of generic FImodules over some field of characteristic P. Okay, so let me sort of describe how this works, how my construction works. So just to give some idea of what these D lambdas look like compared to the stable Specht modules. Okay, so basically I consider these functors between a generic and torsion FImodules, phi and psi, and they're given like so. So if I have an FImodule M, then I want to consider what the FImodule psi of M or phi of M looks like. So at an FI degree N, okay, so psi maybe is a more interesting one because I would like to produce interesting generic FImodules. So what I do is I look at this hom in the category of FImodules, going from the FImodule given by looking at K vector space on maps, the category of FI, so projections, going from some running index to this fixed index N. Okay, so this is, if I don't have the dual, then this is contravariance in the first degree. So that we don't want that, so we have to dualize. And so then this is an FImodule with respect to this running index. And so I can consider what morphisms we get from this FImodule to the FImodule we're given, this M,
I'm a bit lost. What was G and what was T?
Oh, sorry. The T was just meant to be the denote the torsion FImodules,
Okay.
where G is the zero quotient of
the
generic ones.
Okay,
Yes.
okay. So this is Serre's procedure in an explicit form.
Yes. I mean, somewhat. This is like this gives us sort of functors between the category of generic FImodules and the category of torsion FImodules.
Okay.
Yes. I guess the K is just the field here.
Yeah. Okay.
Yeah. So psi should be, if I consider a torsion FImodule, this will provide me with a generic FImodule.
Yeah.
And yeah, I'll say a few words. Maybe I'll go through. I have an example later of sort of precisely what we should be saying, because this is maybe a little bit difficult to see what's going on. And I have an adjoint phi, which is somewhat sort of the same thing up to some functor reality and a tensor product instead of. So in the case of characteristic 0, it actually turns out that these form an equivalence of categories. So that's why we're seeing that. The torsion FI, the simple objects of the torsion FImodules, like I said, will be a spec module sitting in a concentrated in 1 degree. And so the sort of what we get from applying psi to that torsion FImodule will precisely be the stable spec module. So that's why we see that those are the simple objects in the generic category. And this is somehow proved using this Sherwell duality. And in characteristic P, we don't have this anymore. It's not true that these are exact. That these are an equivalence of categories. But they are still adjoints just by tensor homojunction. So we'll get phi is left adjoint to psi. And so how d lambda is constructed categorically is by seeing that if I have example of p regular Young diagram lambda, I'll end up having a surjection going from phi applied to this stable spec module S lambda. And there'll be a surjection from this onto d lambda. So d lambda will still appear as a quotient of this phi of S lambda. Okay, here I'm considering d lambda as a torsion FImodule just existing and concentrated in that degree of the sort of size of lambda. So I can consider an adjoint, that sort of the map we get from the adjunction, which now goes from this stable spec module script S lambda to psi of d lambda. And so it will be non-zero because the beta lambda will be non-zero. And what I'll actually find out is if I look at S lambda in a certain degree, it looks like this spec module associated corresponding to the Young diagram I get by adding a first row. So at each FI degree, it will have this d lambda associated to adding the Young diagram from adding a first row, sitting in it as a quotient. So that also is true on this side, it turns out. And in fact, this iota lambda sends this quotient over in this side to the quotient on this side by an isomorphism. And so d lambda, the script d lambda, this simple generic FImodule comes as the image of this iota lambda. And so in sort of the characteristic 0 case, it's sort of a lot better than this because we actually know what things look like very concretely at each degree. Here, it's sort of a mess. It's sort of very difficult, you'll see later, to compute even small cases of this psi. And it can be hard to see what exactly this iota lambda hits in this image. So Nagpal asks this question, if it's true that for each of these simple generic FImodules d lambda, if it's actually true that each of their components as a representation of the symmetric group will look like a simple representation. for infinitely many of the FI degrees. And so the answer I found out is actually no, that's not true, that if I go high enough, eventually there will be examples where eventually the after a certain FI degree, all of the representations will actually be simple, will be non-simple, so there will be reducible. So here, okay, so exactly like I said, I'll be able to find a Young diagram for a positive characteristic such that in a high enough degree, after that point, none of these d lambda of n will be simple. So here precisely are the Young diagrams which end up working. So this turns out to not to fail in every characteristic. So in characteristic 2, I look at this Young diagram 3, 1, and in sort of characteristic greater than 2, I look at Young diagram with p in the first row and 2 in the second row. So maybe I talk a little bit about what this psi actually concretely does in this positive characteristic case. So I'll just say a little bit about like the proof of this in the case when p is 2, so we can get a sense of how one can calculate with these d lambdas. Okay, so again, let me reiterate the claim. I'm looking at this image of this iota 3, 1. Okay, so in characteristic 2, I have a short exact sequence of representations of sigma 4 going from, so I look at S31 and it has to have, and so 3, 1 is too regular because it doesn't have any double rows. And so a D3, 1 should appear as a quotient of it. And it turns out just by dimension, we end up just with a fixed point sitting in it. So this, again, so like S, the spec module associated to like a row will always sort of just be a trivial representation. In the case of characteristic 2, we'll actually have the D3, 1 itself appears as a spec module associated to this double row 2, 2. And so I claim that I'll calculate this versus psi of D3, 1, in which sort of our simple generic FI module script D3, 1 should sit. And I claim that it can be calculated using this short exact sequence. So we'll have a sub FI module, sub generic FI module, this stable spec module associated to 2, 2. And this will be this co-kernel, so I will have this quotient associated just to the row 2. Okay, so and how this psi will come is I need to calculate it by looking at the induction of this D3, 1, in other words, S2, 2, such that, and I want to only look at terms which do not come from, if I look at the induction of the restriction of S2, 2, so something which comes from the like a restriction to like a smaller symmetric group, and I look at the unit of adjunction which I get from induction and restriction adjunction, and then I want to cancel anything which would come from the induction of that term of the unit of adjunction. So specifically here, you can see from like this Pierre rule. So just if I go down to sigma 3, what I need to do is I just need to delete one box from my Young diagram. And so I get only a one choice, which is this S2, 1. And so now I need to add a box back. So I can do it by putting it on the end or back where it was or on sort of the bottom. So I get these pieces, S3, 1, S2, 2, and S2, 1, 1. And so this S3, 1 will be, so what I have on sort of this side, this S3, 1 will be the quotient piece, and the S2, 1, 1 will be the submodule piece. And so I can see here, I can decompose these further. These aren't simple, except for this middle one. So I write them out as follows. So I have this sort of filtration with these associated pieces, where D3, 1 down here is quotient coming from, because it's a quotient of S3, 1, and this D3, 1 over here turns out to be the sort of submodule, top sort of submodule piece in S2, 1, 1. So there's something to prove, but the unit of adjunction turns out to send this original D31 or S22 isomorphically to this last submodule piece, which appeared in S211. So basically, what I'm seeing is that S22 sits in S211 via the unit of adjunction when we think of it, and the induction of the restriction of S22. Okay, so now I need to calculate this big induction of S22 up to some high degree or some large n. And so what this does is essentially I need to add on a row of n boxes. So I can do this any way I want, but I cannot put two boxes which I'm adding on top of each other. So I have these sort of diagrams are the only choices I can get. And you can see that we cannot fit this bad term, this 211, into either the first or the last one. These first, so this sort of Sn-22 and this Sn-422 cannot come from the induction of this S211. So it's only this middle term which will die when we're taking this limit, which is what we need to do for the psi. And so this is precisely how we get this short exact sequence, because this one is precisely going to be the stable spec module associated to 2, and this one is exactly the stable spec module associated to this 2,2. And so now I need to just to finish. So now this is how we compute psi of D31, but I'd like to really compute this script D31. So I need to recall that I need to look at the image of this iota, which is this map going from the stable spec module S31 into psi of S22. It turns out that it cannot go to this stable spec module associated to 2 part generically, that's always, that every map like that is going to be 0 in the generic category. So in fact, my iota will have to factor through a map going from the stable spec module S31 to S22, which I'm going to call this my kappa. And okay, so I need some more computations of what this psi does. I think this might be the first mistake of the talk. I think this needs to be an empty diagram. Yeah, okay, so it's correct over here. And so essentially, I'm going to try and study this image of kappa. I'm going to prove that since if I can prove that this is not simple, if this is not simple, then because this is an injection, this also won't be simple. The image of the iota. So how I do this is by looking at this co-kernel of kappa. So basically I set up this sort of big diagram of these exact sequences. And so this part from psi of S4 showing that this is sort of the kernel comes from the fact that psi should be left exact because it's a right adjoint, and we have that short exact sequence on the level of spec modules, or in other words, torsion FImodules. And so it turns out that by calculating dimensions, this co-kernel actually needs to be this stable spec module associated to the empty Young diagram. In other words, it's trivial at each degree. Okay, so by my sort of proof, or by my construction of the d lambda, I already think I said that this image already has this constituent factor d n-4 3 1, which comes from adding this first row to 3 1. So we just need to find another d lambda, which is going to sit in my Sn-4 2 2, such that it's not the same as this one, and it's not going to be killed by this co-kernel. So in other words, a lambda such that it's neither trivial nor this n-4 3 1. And so to construct lambda, I use some results again just on the level of representations. So maps, but non-zero sort of maps between spec modules are somehow indexed by these so-called reverse semi-standard tableaus, where I set up sort of this source Young diagram, and I need to color it using numbers occurring the amount of times of like this target Young diagram. So here I have n-4 ones, and then I have 2 2s, and then I have 2 3s. So since I'm running a little bit low on time, I think I'm going to just run through this a bit fast. So this is what works in the case when n is odd. One needs to do something else when n is even, because the Young diagram which we set up won't actually be too regular anymore, but so on and so forth. So this is like the computation of these simple generic FI modules and positive characteristic. But like a sort of another basic thing which you can think about to capture these sort of stable effects is some sort of version of local cohomology, which will sort of be the right derived functor associated to this torsion of FI modules. And so let me go through some computations which I did on that in the integral case. So again, here is a sort of write out of the what the torsion functor will do to an FI module. And again, this local cohomology in the context of FI modules will just be considered to be this right derived functor of this torsion functor. So in over a field of characteristic 0, the local cohomology of the generic stable spec FI modules was calculated by Sam and Stoden, again using this Schur-Weil duality. So going from this sort of FI module context, which is somewhat hard to understand, to the context of GL representations, which is a lot better. But this Schur-Weil duality really is dependent on being over a field of characteristic 0. And so this sort of method can't really be used in, for example, the integral case, or basically any sort of cases which are different from this specific characteristic 0. So my sort of next result is a computation of these stable spec modules for certain choices of lambdas. So here's maybe sort of the silliest warm-up case, which is I'm just going to look at lambda to be this sort of very tall partition 1 1 1 1 1. So a column of length k. And so how should I sort of think about this? These sort of the pieces of the stable spec module in this case. So what it turns out I get is I can consider this Vn, just looking at this quotient of sigma n over sigma n minus 1, so it has dimension n. And I can look at this kernel, Vn twiddle, of the augmentation map. So just by picking some basis here and summing what I have, summing my coefficients to go to z. And so then my kernel, this Vn twiddle, will actually turn out to be this spec module n minus 1 1 for every n. And further, the spec module s n minus k, 1 to the k, will be this kth exterior power of Vn twiddle. Just somehow coming from, if we think about what the generators of the spec module should look like. And so we can see that these x n minus k, 1 to the k, are precisely the degree pieces of the stable spec module associated to lambda. So, like I said, we can consider it like this. Sometimes I'll get rid of this when I'm thinking of it as an FI module. I'll get rid of this index n. And so here's an example sort of case. And so I would like to compute the local cohomology of this s1 to the k. And so what I do is I can look at this. I can even further look at this sort of exterior algebra, lambda v, where where sort of I just look at this direct sum of all the exterior powers. Turns out the local cohomology should be 0 in that case. And I can basically, I can make an acyclic resolution of lambda B using this. And this gives us some computations of the local cohomology of the lambda, this K exterior power of V twiddle, in other words, of this stable spec module associated to this column. So it's sort of what you would expect, just C concentrated in degree 0 when I is K+1, and we don't have anything else. And further, also true for the tensor products. And so since I'm almost out of time, or is it,
No.
should it be 1 hour or 50 minutes?
1 hour.
Okay, sure.
It became 1 hour.
Okay, then I have
Yeah.
Okay, so I can consider, so sort of the case which I calculated is just sort of the barely sort of larger case than this. So I look at these L-shaped Young diagrams, these lambda Ks, which are given by just putting a row of length 2 on top of a column of K-2. But like we saw earlier, the spec modules get bad very quickly. So this is sort of the dumbest L-shaped Young diagram is 2, 1, and we already have this sort of horrible stuff there, these sort of horrible modules. And so I made this calculation of what these, what the local cohomology of these stable spec modules associated to these L-shaped Young diagrams should look like. And it's sort of, I have it written out here. And so maybe some important things to like notice here. So the local cohomology itself is an FImodule. So that's why I have this sort of extra index n running around over here. So as you can see in both sort of the case when K is even and when K is odd, one thing to notice is that this local cohomology is FI torsion. So I don't have any terms when n is over K+1. And I guess here we can see that these actually mostly agree. So the second, so the case local cohomology, the case degree agrees here. It's just a C concentrated in degree 1, and in degree 2 it's almost the same, except so this minus, by the way, is just a sign representation. Except in the case when it's even, sort of this sigma 2 kind of somehow escapes into this third local cohomology degree. Okay, so since I have time, I'll say a few words about the methods of sort of calculating this, which can be generalized further. So basically, it's just my specific methods come from approximating these L-shaped spec modules through the sort of L-shaped spec modules plus extending first row. I can I can approximate these using these sort of warm-up cases, these lambda K of each of those. So just sort of like these hook. And so basically how this is, so basically I need to construct some acyclic resolution of these stable spec modules associated to the L-shaped Young diagrams. And so how this is done is basically I can consider, okay, so I can consider this sort of FI chain complex. So each sort of term is an FI module here. And it's a sort of differential. It looks complicated, but maybe it's actually sort of silly. It's just, we have a tensor and we're just sort of looking at this, just sort of whether or not it sort of already appears. And if it does, then we get this as a sign. And if it does, then it's 0 because, yeah. So maybe like a better description could be, I look at sort of the nth FI degree piece, and I see that, so now I have this basis of V1 up to Vn of V, and essentially what I'm doing is I'm looking at places where it matches, so when I would have a VI tensor VI, and sort of just sending that to VI. So I can describe this differential concretely using just some monkey business with the exterior, with the exterior powers, and I can restrict now, since I really don't want to look at this whole V, just this sort of V twiddle part, I can restrict down to that part specifically. So maybe this differential is sort of a real, just really a description of this D twiddle differential. Okay, so there's more sort of some concrete things we need to do with the exterior, with how things work in these exterior powers. But basically what we see is that mostly these differentials are actually fairly close to surjective in most sort of good cases. So this homology is mostly 0 at all Fi degrees greater than 1. So it really is 0 in that case. But if n is equal to 1, then we have sort of the Z at the end, just sort of due to like degrees sort of breaking down so much. And so the homology there clearly is Z when n is 0, and it's 0 in all other cases. And so how I'll construct, and so basically what I do is I look at this kernel from sending lambda k minus 1 v twiddle tensor v twiddle to lambda k v twiddle in the obvious way. So it forms this sub module of this middle piece, and I can restrict this differential to obtain this following chain complex F from. And this is, I'm going to call this E, and it turns out that this E is actually going to, so I can look at sort of like, I can go one further and I can look at the kernel of this D naught E. And so I'm going to call this is S lambda K prime. And it's going to turn out that S lambda K prime is actually going to be isomorphic to my stable Schweck module associated to lambda K. And so then the theorem follows by computing sort of the chain cohomology of these of this chain complex, this cochain complex, I suppose, of Fi modules at each Fi degree. And then I can sort of feed that, I can use that to compute the local cohomology of this S lambda K prime, and then proving that S lambda K is isomorphic to S lambda K prime. So that this really does compute the local cohomology which we want. So maybe that this sort of cohomology of the cochain complex is maybe too technical to get into here, but we can already see sort of the sort of key players which we want to get in the end already are making a sort of appearance here. And there's some things so why does sort of the chain cohomology, the cochain cohomology of E really give us what we want? So there's a little bit of sort of some monkey business about how local cohomology works here, again, which needs to be done. I can come back to this later, maybe, if there's interest. And basically, sort of the key point of how, of why sort of this is really this S lambda K prime, which we've calculated the local cohomology of, is really what we want, is just using some sort of this formula of Remel. So this is why we can approximate these L-shaped Young diagrams, the L-shaped Young diagrams with the first row by these book-shaped Young diagrams. So here I can see this, and I just sort of plug in my sort of warm-up case to see that this really does give us that this chain complex which we had, this E, its local cohomology really does. We really can compute this local cohomology of S lambda K using that. Okay, so I think I am somewhere in like the 50 to 60 minute range. So I'm going to end my talk there. Thank you very much again.